Mariana Trench, Challenger Deep, the deepest point on Earth. A wound in the Pacific so deep that if you drop Mount Everest into it, the summit would still drown beneath 2 kilometers of freezing water. For centuries, we imagined the deep ocean as a silent, motionless grave. We were wrong. It is a realm of crushing forces, alien biology, and a planetary engine that never stops grinding the Earth from within. We have reached the moon on rockets. We have mapped Mars with orbiters. And yet the deepest place on our own planet remains almost untouched. What secret makes the journey downward harder than escaping Earth itself? To find the answer, we must return to the moment humanity first realized what deep truly means. But this colossal truth was not discovered by modern satellites or nuclear submarines. It was found by a hemp rope and a lump of lead in 1875. The British corvette HMS Challenger was nearing the end of a grueling 4-year mission to map the ocean floor for the first time. For years, the crew had performed the backbreaking labor of sounding, lowering a lead weight until it hit bottom, usually finding the mundane mud of the abyss at depths of 3 or 4 kilometers. But on a routine day, drifting alone in the empty ocean, 2,000 kilometers east of the Philippines, the laws of the geography seemed to break. The weight dropped past 3 kilometers, then 4, then 5. On the wooden deck, crewmen fed mile after mile of cold, heavy rope into the blue, waiting for a slack that never came. They had unwittingly stumbled upon a tear in the planet's skin. The weight finally settled at a staggering depth of over 8 kilometers, marking the discovery of the Mariana Trench. Had they drifted just slightly to the west, they would have found the Challenger Deep, a pit plunging 11 kilometers into the crust. To put that in perspective, beneath their fragile wooden hull lay a chasm deep enough to hide Mount Everest and still have water left over to drown the Alps. They recorded the numbers, but they could not comprehend the violence that created them. They didn't know it yet, but they were floating directly above a massive geological engine that was slowly eating the surface of the Earth. The Earth is not solid ground. It is a restless machine, a puzzle of colossal plates floating on a superheated ocean of magma. While the surface world seems static, the floor of the Pacific is locked in a violent slow-motion collision that defines the shape of our planet. The Mariana Trench is not merely a deep furrow, it is the most active point of a 40,000-kilometer fracture, known as the Ring of Fire. Here, geology operates with industrial ruthlessness. To the east lies the Pacific Plate, a massive slab of oceanic crust. To the west is the Philippine Sea Plate. These two titans do not simply sit beside one another, they are engaged in a grinding mechanism called subduction. The Pacific Plate, driven by thermal currents deep within the mantle, is being forced to bow down. It slides beneath the lighter Philippine Plate, descending into the Earth's interior to be melted and recycled. This is not a smooth conveyor belt. It is a chaotic interface of friction and stress accumulation. As the plates grind together, rock faces kilometers deep lock up, storing elastic energy, like a planetary spring, until the rock snaps. These ruptures release megathrust earthquakes events, so powerful they release more energy than thousands of nuclear warheads, reshaping the ocean floor in seconds. This zone of destruction is the engine room of the planet, creating the volcanoes that rim the Pacific and carving out the chasms that plunge into the abyss. And beneath the intersection of these forces, where two tectonic plates are locked in a cycle of crushing and recycling, is the point we are about to pass. One of Earth's best-kept secrets is that rocks have a lifespan. The continents are ancient rafts that persist for billions of years, but the ocean floor is transient. The Pacific Plate entering the trench today is approximately 170 million years old. It was born in fire when the supercontinent Pangaea first ripped apart, and it has spent eons traversing the globe, cooling and contracting as it moved away from its heat source. By the time it reaches the Mariana Trench, this crust is old, cold, and incredibly dense. Gravity takes hold of this dense slab, dragging it down into the hotter, lighter mantle below. This phenomenon, known as slab pull, is the primary force driving plate tectonics. The Mariana Trench exists because this ancient slab is falling off the edge of the world, steepening its angle of descent. as it dies, creating a vertical tear in the crust that reaches deeper than anywhere else on Earth. Geology tells us why the abyss exists. It is a graveyard for the planet's oldest ocean crust. But to understand the reality of that depth, we must leave the academic theories behind. We must do what sunlight cannot leave the surface world and execute the descent. As you execute the descent, the first casualty is color. The visible spectrum begins to collapse the moment you slip beneath the waves. Red light is absorbed within the first few meters, followed by orange and yellow, until the world is reduced to a monochromatic, suffocating blue. In these first 200 meters, known as the epipelagic or euphotic zone, we are still within the domain of the sun. It feels familiar here. This thin layer is the lungs of our planet, where phytoplankton power the photosynthetic machinery that generates half the oxygen we breathe. It is the starting line of the oceanic food chain, teeming with zooplankton, tuna, and whales. But as the mission depth increases, we cross an invisible threshold into the mesopelagic, the twilight zone. Here the sun is no longer a source of heat, but a fading memory. The temperature plummets, and the light becomes too weak to support photosynthesis. Yet the biomass readings here are staggering. This zone is patrolled by the bristlemouth, a small fish with spiny teeth, that despite its size is likely the most abundant vertebrate on Earth, numbering in the quadrillions. They are the gatekeepers of the deep, existing in a perpetual dusk, where the ocean floor is still kilometers away and the surface feels like a different planet entirely. And when the last photon of sunlight vanishes, you discover the most terrifying truth about the deep ocean: it is not empty. It is watching. We have entered the bathypelagic, or the midnight zone, beginning at a depth of 1,000 meters. Here the rules of human perception shatter. In this sensory void, human eyes are rendered useless. There are no reference points, no horizon, and no direction. To survive here, biology has been forced to engineer new forms of vision. Evolution has taken two divergent paths in this darkness. Some creatures, like the barrel-eye fish, have developed upward-pointing eyes to catch the faintest silhouettes against the gloom above. Others have abandoned sight altogether. In this pitch-black environment, most predators hunt, using a biological sonar system, a series of pressure sensors along their bodies known as lateral lines. They map the 3D space around them, not with light, but with the tremors of the water itself. They can feel your heartbeat through the hull before they can see you. The only light here is artificial, generated by the creatures themselves. Bioluminescence becomes the primary language of the deep. But in a world of absolute darkness, a light is rarely a beacon of hope. It is almost always a trap. The anglerfish dangles a glowing lure in the void, a biological decoy designed to attract prey into a maw of needle-like teeth. As we descend further, the phenomenon of deep-sea gigantism takes hold, where isolation and scarcity drive species like the giant squid to monstrous proportions. We are now drifting through a world that covers more than half the planet's surface, yet remains a mystery. The temperature has stabilized at a near-freezing 4 degrees Celsius, but darkness is merely a psychological threat. As we cross the 6,000-meter mark, we face a new, tangible enemy. The water outside is no longer just a medium. It has become a crushing weight, and we are entering the zone where biology battles physics for the right to exist. Welcome to the Hadal Zone. Named after Hades, the Greek god of the underworld, this is the oceanic frontier that begins at 6,000 meters and descends into the planet's deepest scars. At this depth, water ceases to be a welcoming environment for life and transforms into a hostile, crushing force. We've crossed a physical threshold where the ocean behaves less like a liquid and more like a hydraulic vise. The environmental parameters here are set to critical. The temperature hovers just above freezing, maintained by cold currents flowing across the ocean floor all the way from Antarctica. This global conveyor belt of freezing water is crucial, supplying oxygen to these depths, but it also creates a world of perpetual chill. However, cold is manageable. Pressure is the true enemy. At the bottom of the Challenger Deep, the hydrostatic load reaches approximately 1 Ozu 86 bars, more than 1,000 times the atmospheric pressure at sea level. To visualize this, imagine the weight of an oversized pickup truck balanced on the tip of your thumb. Or in aerospace terms, the pressure here is roughly equivalent to being inside a combustion chamber at the moment of ignition. For a biological organism, this kind of pressure doesn't just crush bone, it fundamentally alters chemistry. Under this load, fluids, compressed gases turn into liquids, and the very molecular machinery of life is threatened with total structural collapse. According to standard biological models, this zone should be a dead world, the silt covering the floor churned by seismic activity, and unseen currents should be barren. Yet the anomaly of the Mariana Trench is that it is not a grave. Against all physical logic, life is here? How does life exist in a place where physics dictates it should be obliterated? The answer lies in the existence of biological anomalies, creatures that have abandoned the blueprints of surface life to become masterpieces of deep-sea engineering. The first thing you notice in the silt is the xenophyophores. To the untrained eye, they look like fragile lumps of rock or jelly, some growing as large as a football, exceeding 20 centimeters in diameter. This size is biologically illegal for a single-celled organism on the surface. Cells typically remain microscopic because they rely on passive diffusion to move nutrients and waste across their membranes. If they get too big, they starve or poison themselves. Yet in the Hadal Zone, xenophyophores defy the square-cube law. They are single-celled giants, living contradictions that thrive in the crushing dark, filtering the silt for trace nutrients. They are as alien to us as any organism we might hope to find on Europa. Then there are the ghosts of the trench, the Mariana snailfish. These are the deepest known fish in the ocean, found at depths where the pressure is intense enough to warp steel. They do not look like the fish we know. They have no scales to weigh them down. Their skin is translucent, revealing the internal organs and muscles working beneath. They possess no swim bladder, the gas-filled sac most fish use for buoyancy, because at 1,000 atmospheres, any gas cavity would be instantly imploded. Instead, their bodies are filled with a gelatinous substance that matches the density of the surrounding water. They do not fight the pressure, they become one with it. Alongside them are the scavengers, giant amphipods, and translucent sea pigs. In the upper ocean, amphipods are millimeter-long specks. Here, deep-sea gigantism swells them to the size of a human hand. They scour the floor for marine snow, the decaying organic detritus that drifts down from the world of light miles above. But marine snow is scarce. Very little edible matter survives the 11-kilometer fall without being eaten by something else. This scarcity has driven the evolution of a secondary alien energy source. The true secret of the Hadal biosphere isn't its monsters, it's its chemistry. In the shallow waters, life is a solar economy powered by photosynthesis. Down here in the eternal black, life has switched to a chemical economy. We see sprawling mats of microbial ooze coating the rocks near the fault lines. These are not powered by the sun, but by the earth itself. They utilize chemosynthesis, harvesting energy from hydrogen sulfide and methane seeping out of the crushed rocks of the subduction zone. This is a biosphere that does not need a star to exist. It is a closed loop feeding off the geologic heat and chemical blood of the planet. But the most sophisticated engineering is invisible to the naked eye. It happens inside the cells. High pressure usually kills by forcing water molecules into the intricate folds of proteins, causing them to unravel and lose their function, a process called denaturation. If your proteins unfold, your metabolism stops and you die. To defeat this, Hadal creatures have evolved a biochemical armor. Their cells are saturated with a molecule called trimethylamine N-oxide, or TMAO. This is a piezolyte, a pressure-counteracting solute. TMAO molecules act like microscopic pillars within the water structure of the cell, forcing water molecules to bond strongly with proteins, essentially taping the protein structures together, so they cannot unravel under the crushing weight. This is a delicate chemical gamble. The deeper a fish goes, the more TMAO it needs to keep its cells from collapsing. But there is a limit. At a depth of around 8,200 meters, the concentration of TMAO required to counteract the pressure makes the fish's cells saltier than the seawater outside. At that point, osmosis reverses, and water would rush into the cells to dilute the salt, causing them to swell and burst. This is the theoretical death line for fish. The Mariana snailfish lives right at this edge, a biological machine tuned to the absolute limit of what physics allows. They do not survive here because they are tough in the way a tank is tough. They survive because they have rewritten the laws of biochemistry to turn the ocean's pressure into a structural component of their own bodies. They have had millions of years to perfect this adaptation. We, however, do not have that luxury. If evolution had millions of years to engineer the biochemical armor of the snailfish, humanity has had less than a century to develop a countermeasure. Biology fights pressure with chemistry. We fight it with mathematics and metallurgy. To understand the sheer audacity of reaching the Challenger deep, we must reframe the challenge. We often compare deep-sea exploration to space travel, but from an engineering perspective, the abyss is infinitely more hostile. When we build a spacecraft, the hull must withstand a pressure differential of 1 atmosphere, the air inside pushing out against the vacuum of space. It is a tension problem. But when we build a submersible for the Hadal Zone, the hull must withstand a pressure differential of over 1,000 atmospheres pushing in. It is a compression problem of astronomical proportions. At 11 kilometers down, the ocean is trying to crush a submersible into a sphere of scrap metal the size of a basketball. Standard materials fail. Air tanks, the staple of scuba diving, would detonate. Even military nuclear submarines, the apex of naval power, are generally rated to crush depths of only 500 to 1,000 meters. To go deeper requires a complete redesign of what a vessel is. The solution is the sphere. It is the only geometric shape where pressure is distributed perfectly evenly across the entire surface structure. But the sphere must be buoyant. Since you cannot use air tanks to float, engineers use syntactic foam, a composite material made of billions of microscopic hollow glass spheres suspended in epoxy resin. It is the fuel of the deep, providing lift without collapsing under load. But the physics of the abyss are unforgiving. In space, a small leak might be manageable. Here, there is no such thing as a leak. A structural failure at this depth results in an instantaneous, catastrophic equalization of pressure. The margin for error is not small. It is non-existent. Recent tragedies like the implosion of the Titan submersible at a fraction of this depth serve as grim reminders that physics does not care about innovation or hubris. It demands absolute structural perfection. The ultimate test of this engineering philosophy occurred on January 23, 1960. It was not performed by a modern autonomous robot, but by 2 men sitting inside a steel ball suspended beneath a giant tank of gasoline. Don Walsh, a U.S. Navy lieutenant, and Jacques Piccard, a Swiss oceanographer, climbed into the Trieste. It was a bathyscaphe, essentially an underwater dirigible. The descent was a slow 5-hour freefall into the dark. As they passed the limits of sunlight and entered the midnight zone, the temperature inside the sphere dropped to a shivering 7 degrees Celsius. They were effectively piloting a refrigerator into a hydraulic press. At a depth of 9,000 meters deeper than anyone had ever gone, silence was shattered by a violent, thunderous bang. The entire vessel shuddered. In a survival scenario, this is the moment of panic. But Walsh and Piccard were piloting a prototype in an alien environment. Panic was a luxury they could not afford. They scanned the instruments. No water entry. Systems nominal. But the sound had been real. They eventually located the source. The outer plexiglass window of the entry tunnel had cracked. Under the immense load, the stress differential between the steel hull and the acrylic window had caused a fracture. They faced a critical decision: abort the mission or trust the physics. They knew the window was conical, shaped like a cork. The deeper they went, the harder the ocean would push the cone into its seating, theoretically sealing the crack tighter. It was a gamble on the fundamental laws of mechanics. They chose to continue. They descended for another 2,000 meters, listening to the groaning of the steel as the pressure climbed to 1.1 tons per square centimeter. Finally, at 10,911 meters, they touched down. A cloud of ivory-colored silt billowed up, obscuring the view. When it settled, illuminated by their quartz arc lights, they saw the impossible: a flatfish, later debated to be a sea cucumber, shifting across the sediment. Life was here. They stayed for only 20 minutes. The cracked window held. The steel sphere held. But as they began the 3-hour ascent back to the world of light, they carried with them the realization of what they had achieved. They had not just survived a dive, they had successfully executed a manned mission to the most hostile environment on Earth, relying solely on the integrity of their calculations against the crushing weight of the planet. It was a feat of endurance that would not be repeated for another 52 years. There is a final paradox to consider. We have mapped the topography of Mars with higher resolution than the floor of our own Pacific Ocean. We calculate the trajectories of comets and hunt for signals from distant stars, yet the dark heart of our own planet remains a blank page. To date, scientists have identified only around 400 species in the Hadal Zone. But this low number is not evidence of a barren world. It is evidence of our own blindness. Most of our exploration has consisted of extreme tourism or rudimentary science tying bait to a lander, dropping it into the silt and filming whatever swims into the narrow beam of a spotlight. Imagine trying to understand the complexity of the Amazon rainforest by dropping a bucket into the canopy at night and seeing what crawls inside. That is the current state of deep-sea exploration. We are missing the bigger picture. The Mariana Trench is not just a geological curiosity or a grave for old tectonic plates. It is a laboratory for the impossible. The genetic codes of the creatures living here, organisms that fix carbon without sunlight and stabilize proteins against crushing pressure, hold the potential for breakthroughs in medicine, biotechnology, and material science. Furthermore, the hydrothermal vents hidden in these trenches are the strongest candidates for the cradle of life itself. Before there was photosynthesis, there was likely chemosynthesis. To explore the trench is to explore the origin of us all. We look to the stars to find our future, and we look to moons like Enceladus to find alien life. But we often forget that the most alien, hostile, and scientifically rich frontier is not millions of miles away. It is right here 11 kilometers beneath the waves. The ocean is not a pool to be swum. It is a universe to be explored. And in the eternal darkness of the Challenger Deep, where the weight of the world tries to crush everything into oblivion, life has delivered its final defiant message. There is no environment so harsh that it cannot be conquered. The surface is just the beginning. The real Earth is waiting in the dark.